So the last thing we're going to have from this unit, this chapter, is a look at what are called binomial distributions, where to start, we're going to get the idea of what a binomial experiment is. And the name binomial should kind of imply the flavor that we're seeing here. We're looking at situations where we have one of two outcomes. Either what we're measuring happens, we call that a success, or it doesn't, and we call that a failure. And I'll see what that means with a bit more of an understanding of how that language is loaded in a second. But essentially, we have one of two outcomes, hence bi meaning two in the name. Where for a binomial experiment, we have a couple of properties and some notation to set. Where for one, we're always running n trials. That is, we have a fixed number of runs on whatever we're doing. So if I'm going to take a coin flip, a series of coin flips, as my binomial experiment, because there's obviously only two things that can happen. Either I land heads or land tails. Well, obviously, it's stretching it a little bit, but you get the idea. I'm not going to keep flipping the coin forever and ever. I might flip it 5 times, I might flip it 10 times, I might flip it 100 times, but I have a fixed finite number of times that I'm going to flip the coin. I have a fixed finite number of trials. And in those trials, we have two possible outcomes, either a success or a failure, where, as I said, you kind of get the implication that a success is going to be good and a failure is going to be bad, but really what that means is we are seeing what we're trying to measure or we aren't. So sometimes a success can actually be a good thing. Like we might want to talk about the probability of 10 people being able to find their true love, whether that's a guy, a gal, or some non-binary pal for that matter. We're talking about something that most people would consider a good thing. I guess some aren't really fans of romance, that's possible, but generally we like to find happiness, so I would consider that a success. We could also have something that's not quite a good thing or a bad thing, it's just kind of a thing, like the probability of running into 5 people and all of them having seen the most recent Marvel movie, which I think was a Spider-Man, but I can't really remember, and it's probably worse than Into the Spider-Verse, and that's all I really care about in that context. But, it's a good thing, I suppose, for the mouse, though whether good things happening to the Disney Corporation is debatable for most people, I would say that at the very best, it's pretty benign as far as general life goes. So, a success being someone having seen the most recent Marvel movie doesn't necessarily mean anything, it just means that we find someone who has. And then they can also be things that would generally be considered explicitly bad. If we're trying to study Holocaust denial, we could find the probability of running into someone who denies that the Holocaust happened. I don't think I need to explain to you why that's explicitly a bad thing that someone denies the Holocaust, but in that context, because we are specifically trying to study that, it would be considered a success. It's merely what we're looking for, not necessarily a good thing, just what we mean to observe. From there, we have that these probabilities are consistent. That is, the probability of success is some value p, and it's always that value p. The trials that we run are independent and identically distributed. That is, if I get a success on the first one, it means nothing to getting a success on the second one. It makes it no more or less likely. And then also, we have probability q for failures, where, because these things are binomial, there are inherently one of two options. The probability of failure is always 1 minus p. And then finally, a bit of notation there, that when we're talking about these things in terms of random variables, our random variable x is always defined in terms of a number of successes. So if you want to find the probability of x equals 3, for example, that means we're trying to find 3 successes in particular. So for a quick and, I think, kind of straightforward example, we can talk about that coin flip where, let's say that what I want to find here is a number of heads in 5 flips. So I'm going to flip the coin 1, 2, 3, 4, and 5 times. And I want to count the number of heads, even though I didn't pay attention for the sake of that visual. But looking at that, we would have that in terms of these properties, n equals 5 trials, a success is getting heads, failure is tails, and in terms of our probabilities, P, the probability of getting heads, is 0.5, or if you prefer 1/2 as a fraction, while Q is also 1/2 because we're going to pretend that landing on its side doesn't happen. It's usually what we do with coins because, well, it's pretty rare. But those are our options there, where x is some number of heads in 5 trials. So, for one example of what we could do with this in terms of a probability, what we could say is we want to find something like the probability that x is equal to 3. That is the probability of tossing the coin 5 times and getting precisely 3 heads. Well, to do this, what we can understand is we want to get 3 successes out of 5 trials. I always say that backwards. And it doesn't really matter what order we select them in. We just need to get them somewhere, whether it's 1, 3, 5, 1, 2, 3, 3, 4, 5, 2, 4, 5, whatever it happens to be. They're all the same as long as we get 3 of them. So we've got 5 trials, and we're going to pick 3 of them to get our successes in. So we've got 5, choose 3 ways to get those 3 successes. And then with those, we have to understand that we have a probability of getting any one success is 1/2. So if we need 3 of them, the probability of getting all 3 is 1/2 to the third. And then finally, we kind of care about what happens in the other 2, because we specifically want 3 heads. We don't want 3 or more. We don't want 3 or fewer. We want exactly 3. So we need those other 2 to be failures. It just happens that the other 2 being failures looks a lot like the other 2 being heads in terms of a probability, but, well, there's a 1/2 chance of getting 1 tail. So there's a 1/2 times a 1/2 chance of getting 2 of them. Which means if we want to get the probability of exactly 3, we're picking our options. We take the number of ways to get what we want with their probability associated, and then we have the ones that are left over with their associated probability. And we'll see later that this is actually the general formula for a binomial probability. And there's also ways to do this in the calculator too, but that's later on in this section. For now, main thing to get is that our probability here would be 0.3125, about 31% chance that if you flip a coin 5 times, you'll get exactly 3 heads out of that, using really a combination of the multiplication rule taken 5 times and some just a bit beyond fundamental counting. Where the next thing we're going to do, the next thing we're going to look at, is how we can actually identify our probabilities, not just in terms of these numbers, but whether or not what we're working from even happens. That is, how we can identify whether or not an experiment truly is binomial, and that is that these things will apply.